In the first segment of this talk, we have mentioned that depth cameras may generate invalid depth measurements. When we project the depth information onto the 3D point cloud, it leads to many unique challenges in 3D geometric data understanding. Some of the challenges we will list in this page to start our second half of the technical discussion. These challenges include inferring 3D using minimum number of images, accurate dense reconstruction for virtual augmentation, complete 3D model without holes, shareable and editable space models for multi-users, augmentation of human users as realistic avatars, and finally, privacy and standards using shareable 3D data. Today's tutorial will provide to our audience actionable information to address the first 5 challenges. But although the last challenge is equally important, we will not touch this topic in this tutorial because any solution to privacy and standards when sharing 3D data will go beyond the scope of a software library such as OpenARK. First, let's focus our discussion on the challenge of automatic shape retrieval and completion. Since earlier we have emphasized that RGBD sensors tend to obtain incomplete models of objects from 3D space. For instance, when we use a time-of-flight camera to acquire a 3D model of a chair, as rendered on the right, some part of the object in space then can be easily missed from the acquired 3D model. This may be due to a variety of reasons, such as measurement noise, occlusions, distance limitations, or material properties of the object. Then our task on such incomplete data will be to complete the 3D objects for actual virtual augmentation. If we look at this problem from 30,000 feet, there are 2 very well understood approaches. The first approach is to modify the noisy point cloud with the expectation to clean up the data and have the point cloud to match with the ground truth 3D model. For instance, the well-established iterative closest point, or ICP, Hoff transform, and ransack all belong to this approach. However, if we are familiar with these algorithms, you may recall the following drawbacks. Number 1, in AR applications, our 3D model knowledge will never be exact to match real object point cloud. For example, we may have a 3D model from the chair category, but we cannot possibly have exact models for every type of chairs. This fact has been established as a key sticking point even in image classification challenges. Second, 3D point cloud are unordered and randomly sampled. Therefore, it is difficult to solve for exact point-to-point correspondence between 2 point clouds. Number 3, even if we can solve for a stable matching for rotation and translation, the transform point cloud will still retain scan holes, and the above algorithms lack the information about how the scan holes should be compensated. Therefore, in 3D shape completion problems, using deformable CAD models are becoming more popular for real-world scenarios. The typical goal of using deformable CAD models, as we illustrated on the right, is to define objective functions and effective operators to deform a representative categorical 3D CAD model to fit the noisy point cloud observations. Advantages of this approach are manifold. Number 1, the algorithm preserves the noisy measurement but choose to operate on cleaned model data, which will be better conditioned to apply any deformation. Number 2, deformed model tends to automatically fill up holes from the measurement data. And number 3, And most importantly, using deformed CAD models does not require exact matching of the model shape with the real object shape. Next, let me present a short journey about our experience in finding a good solution to match 3D object shape and simultaneously complete missing shape point cloud data. To begin, we need to choose a good CAD model database with sufficient semantic annotation. We have chosen ShapeNet from Leo Gibas Group at Stanford as our reference library, which is a richly annotated large-scale dataset of 3D shapes. Due to the fact that a CAD model library does not intend to represent exact shapes of all the objects in the same category. For example, on the right, ShapeNet enrolled different CAD models under the same chair category, but only when those 3D models are sufficiently different in their shapes, then they will be enrolled in the ShapeNet. Therefore, these models are in the library are typically normalized in a unit cube instead of preserving their real size. So when using these models, there is one additional dimension of unknown scale that we need to estimate and rigidly transform into. In addition to the model categories, ShapeNet metadata also provide annotation for where is the upright and front directions, if an object contains parts, and if an object contains symmetry, etc. Our investigation into this problem started with trying to reproduce another paper from Leo Gibas' lab called Learning Representations and Generative Models for 3D Point Clouds in 2017. In this paper, the authors proposed an autoencoder network to estimate a latent representation, H, of the deformed CAD model space, which minimizes the reconstruction error, where the FH is the 3D shape reconstructed by the decoder portion of the network based on the latent variable H, while H is also estimated from the input noisy point cloud data to represent the deformed CAD model space. Therefore, H is called the latent code for representing a family of input shape data. In the paper, the authors gave a few validation examples, such as being able to complete point cloud with missing parts, and being able to use H as feature vectors for shape classification. However, in our experiment with augmented reality immersive applications in mind, we found that the proposed objective function tends to generate deformed mesh models that contextually not plausible or visually not pleasing, such as one example provided on the right. This type of results may very well have minimum reconstruction error and also may correctly identify the right category, in this case as in the chair category, but it does not fulfill our goal for augmented reality applications to provide visually pleasing 3D complete shape from the point cloud with the missing data. To address this problem, from our research, we believed introducing an intermediate continuous function of sign distance function can successfully improve the quality of this shape completion approximation. For those of you who have not used sign distance function before, it is an extension of the definition of a level set. For a shape S, a sign distance function can be evaluated at any 3D coordinates x. And it is simply defined as if x is inside the shape S, then its sign distance function is negative shortest distance from x to the boundary of the shape S. If x is outside the shape, then its sign function is the positive value of the shortest distance, d. It is easy to check that from the definition. Sign distance function is a continuous function. The magnitude of its gradient is always equal to 1, and on the boundary, this gradient of the sign distance function is equal to just the normal vector. Then in the paper published at the CVPR 2019, Jung Park and co-authors propose a deep autodecoder network to approximate not just the point cloud, but the continuous sign distance function phi that is compatible with a category of shapes, such as chairs, tables, cars, etc. The use of this latent shape variable is very important, because if we do not simultaneously optimize this latent shape variable, then each autodecoder network will only correspond to a fixed shape of CAD model, and it loses the generality to be deformed to approximate a category of different shapes. With the added input dimension of this latent shape variable, we can then use training shapes to optimize the autodecoder network parameters, such that given a training shape S, there exists a one-to-one correspondence between the Z value to the training shape S and its corresponding sign distance function. For instance, let's go over one way to optimize both the autodecoder network and the latent shape variable Z. During the training, we can assign n distinct codes from Z1 to Zn for the n distinct shapes from S1 to Sn, such that the same autodecoder network can minimize the difference between the given shape's sign distance function and the network's output value. Then during the testing, of course, the network parameters now will be fixed. An algorithm will solve for the optimal Z in its latent space that may also minimize the observed point cloud's average sign distance function. And we can see that when the deformed CAD model is an exact fit on the observed point cloud, then the total difference function should be very, very small, close to 0. That's the objective function that we are trying to minimize. Without going into more details about the implementation, which is provided in one of our papers in 2020, called Extending Deep SDF for Automatic 3D Shape Retrieval and the Similarity Transform Estimation. We can summarize our proposed joint shape retrieval and transform estimation algorithm as follows. Number 1, the shape completion problem is formulated as finding the optimal Z star given trained autodecoder network parameters and the partial observation point cloud from x1 to xk. The network can approximate any number of points in unordered fashion, which was a major sticking point for optimizing in point clouds. In fact, the autodecoder network can generate a continuous sign distance function for any 3D point, not just at the sampled point cloud that could be incomplete. Number 4, evaluation of the sign distance function does not require the encoder part. Once we recognize that, then during the training, we also do not need to train a set of deep neural network parameters for the encoder network. Potentially can make the optimization faster and more stable. Finally, we said the most important property of the estimated scientist function is that it represents deformable CAD models. The model boundary of the deformed shape is simply the zero set of the estimated scientist function. This zero set from the continuous scientist function will yield object surfaces that are more complete and visually more pleasing than compensating the noisy point cloud or its mesh model. In this page, we will show a comparison of compensated object shapes using some test shapes on the left. The red color indicates measured samples, and the gray color indicates estimated deformed CAD model, superimposed. And we can see that our proposed method fits a lot better than the existing other methods, both for completing the missing data and for estimating the optimal pose and scale of the CAD model in 3D space. And you can compare the quality of each of these 4 example scans. The last topic we will discuss in this talk is about 3D avatar modeling, which is another function that is very important for realistic virtual immersion experience. In the literature, most people are familiar with the 3 main directions, namely using skeletal model, using fully articulated model, or using deformable avatar models. In particular, when affordable, deformable avatar modeling is preferred, including in the applications of video games, social media, telepresence, and the human simulator for medicine training. In the literature, tracking deformable human avatars can be achieved by either an offline multi-camera system to capture all the light field from 360 degrees. However, for most mobile AR applications, it is more desirable to use solutions that are real-time and only require a single camera. So this is the scenario we are interested in OpenARK. Then we can summarize the existing literature in 3 directions, including template-based, based on body skeleton or silhouette, model-based, such as the simple model, and the freeform, such as Kinect fusion or dynamic fusion. In OpenARK, we have chosen a hybrid model aiming for extracting a low-dimensional model, fast solver, and model fusion. Using low-dimensional models increases estimation robustness and speed for working a low-dimensional space. Most of our AR systems have limited compute budget, so the existence of fast solvers will help with the real-time performance on low compute devices. And finally, our model fusion will combine both 3D depth plus 2D RGB image information for enhanced realism and robust tracking. First, let me play a short demo video created by our lead student researcher, Bill Zhou.
In this demo, we will show a model-based, fully deformable human avatar reconstruction system based on a single RGB camera feed. This will be available as a module in OpenARK, which will help AR devices better understand the human body and its interactions with other real-world objects. We begin with a linear, low-dimensional model of the human body called a symbol. The model consists of joints and shape keys which can adapt to any body type. Given a single RGBD observation, we attempt to fit a parameterized model to the depth image. The model-based tracking allows us to infer missing points. Gangnam Style. Gangnam Style.
The real-time avatar tracking is achieved by using fast solvers to minimize the following joint models. First, we will be minimizing the standard ICP error between the measured point cloud and the physical model. And second, we will minimize the body joint prior. This is done by running a neural network model. Finally, we also minimizes a pose prior, which is a learned probabilistic model based on human pose knowledge, namely which body pose configuration has high probability and which configuration has low probability. In particular, in our algorithm, we have adopted OpenPose as a neural network model to anchor the joint positions of our video streaming data. Due to the fact that our algorithm was developed initially based on the Intel D435 camera, its depth signal could be quite noisy, as we have shown in the video and also a screenshot in here. So, directly optimizing a deformable avatar model in the depth map data will be prone to error. To mitigate this problem, we used the correspondence between the depth image and the RGB image, one-to-one, pixel-to-pixel correspondence. And then we first use OpenPose to identify the best skeleton joint positions in the RGB image. Then feeding the deformable avatar model in the corresponding depth data positions can be initialized from a good guess. Then our algorithm in real time will iteratively retrieve a new frame. Upon receiving its RGB image, a joint prior will be fitted in the image space using the OpenPose. These joint positions will be used to minimize the post-prior error and the ICP fitting error. For more information, please refer to our code in the OpenARK repository. Okay, this will complete our first talk. And if you have any questions, we are happy to continue to answer your questions for the remainder of the time.